Organic matter in domestic wastewater, GCODPD, personal care 5.25%. Anaerobic waste treatment. An overview historical development. Mainly used for reducing mass of high solids wastes, e.g. human waste, night soil, animal manure, agricultural waste and sludge. Early applications of anaerobic waste treatment include Mora's automatic scavenger, cited in French journal Cosmos in 1881. Septic tank developed by Donald Cameron in 1895. England. Imhoff tank, developed by Karl Imhoff in 1905. Germany. Manhole for sludge cleanout. PS PETS sludge drying bedmark ground surface wastewater from greater than F house sludge. Septage. Aerobic treatment process, considerable progress in short span of time. Anaerobic technology. Energy crisis in 70s and 80s. A renewed interest in anaerobic process. WN pound less than an A degree 2 anaerobic treatment plants for industrial applications. Source: Franken, 2001. Anaerobic waste treatment definition. Anaerobic treatment is a biological process carried out in the absence of O for the stabilization of organic materials by conversion to CH and inorganic end products such as CO and NH. Anaerobic microorganisms. Organic materials plus nutrients CH plus CO plus NH plus biomass. Anaerobic processes. Anaerobic fermentation. Anaerobic respiration. Acidogenesis overview. Anaerobic biodegradation. Complex organic matters on proteins, carbohydrates, lipids no greater than S11. Tc greater than C equals amino acids, sugars, fatty acids, alcohols. A intermediary products 8. C greater than 2. Propionate, butyrate, etc. 4 CCUD greater than U tilde tilde OOU acetate hydrogen. Carbon dioxide S homoacetogenesis co ZXP, leg. XOWO, EY. May in, ag methanogenesis. Kinetic parameters. Anaerobes. Growth kinetics of methanosarcina and methanosata 0.20 less than A plus less than greater than methanosata methanosarcina UV. Asterisk. AAGY 0.12 radians GA and 0.08 Re UV7 SOSE, hash. ZA 0.044 inches 6A plus 0.00 plus. 50 quadrillion 100 trillion 150 billion 200 million 250,000 300 acetate concentration. mg cod, L. Cod balance aerobic anaerobic biodegradation tilde OS. Essential conditions for efficient anaerobic treatment. Avoid excessive air, O. Exposure. Scent. No toxic inhibitory compounds present in the influence. Scent. Maintain pH between 6.8 7.2. Scent. Sufficient alkalinity present. Scent. Temperature around mesophilic range 30 to 38 degrees Celsius. Enough nutrients, N and P, and trace metals especially Fe, Co, Ni, etc. Cod, N. P equals 350 to 7, 1. For highly loaded system, 1000 to 7, 1. Lightly loaded system. Environmental factors. The successful operation of anaerobic reactor depends on maintaining the environmental factors close to the comfort of the microorganisms involved in the process. Temperature 2 to 100 thermophiles 8 psychrophilic. 5 to 15 degrees Celsius. 0 and 4% 60 mesophiles mesophilic. 35. 40 degrees Celsius. At 40. 8 psychrophiles thermophilic. 50 to 55 degrees Celsius. F209000204060 temperature. Degree C. Rule of thumb. Rate of a reaction doubles for every 10 degree rise in temperature. Activity 13 1.040840.540.340.0 picohenries. Relative activity of methanogens to pH range for acidogens is 5.5 to 6.5, methanogensis 7.8 to 8.2. Operating pH for combined cultures is 6.8 to 7.4, with neutral pH being the optimum since methanogenesis is considered as a rate-limiting step. It is necessary to maintain the reactor pH close to neutral. Nutrients and trace metals. All microbial processes including anaerobic process requires macro, N, and S, and micro, trace metals. Nutrients in sufficient concentration to support biomass synthesis. In addition to N and P, anaerobic microorganisms, especially methanogens, have specific requirements of trace metals such as Ni, Co, Fe, Mo, Se, etc. The nutrients and trace metals requirements for anaerobic process are much lower, as only 4 to 10% of the cod removed is converted biomass. Cod. N. P equals 350 to 7. 1. Inhibition. Toxicity. The toxicity is caused by the substance present in the influent waste or byproducts of the metabolic activities. Ammonia, heavy metals, halogenated compounds, cyanide, etc., are the examples of the former type, whereas ammonia, sulfide, VFAs belong to latter group. Comparison between anaerobic and aerobic processes. Anaerobic organic loading rate. Aerobic high loading rates. 10 to 40 kg cod per meter % day. For high-rate reactors, e.g. AF, UASB, EFBR. Biomass yield. Low biomass yield. 0.05 to 0.15 kg VSS per kilogram cod. Biomass yield is not constant but depends on types of substrates metabolized. Specific substrate utilization rate. High rate. 0.75 to 1.5 kg cod per kilogram VSS day. Startup time. Long startup. 1 to 2 months for mesophilic. 2 to 3 months for thermophilic. Low loading rates. 0.5-1.5 kg cod per meter degree day. For activated sludge process, high biomass yield, 0.37 to 0.46 kg VSS per kilogram cod. Biomass yield is fairly constant irrespective of types of substrates. Metabolized, low rate, 0.15 to 0.75 kg cod per kilogram VSS day. Short startup, 1 to 2 weeks. Continue. Anaerobic aerobic SRT. Longer SRT is essential to retain the slow-growing methanogens within the reactor. Microbiology. Anaerobic process is multi-step process and diverse group of microorganisms degrade the organic matter in a sequential order. Environmental factors. The process is highly susceptible to changes in environmental conditions. SRT of 4 to 10 days is enough in case of activated sludge process. Aerobic process is mainly a one-species phenomenon. The process is less susceptible to changes in environmental conditions. Advantage of anaerobic process. 1. Less energy requirement as no aeration is needed. 0.5 to 0.75 kWh energy is needed for every 1 kg of cod removal by aerobic process. 2. Energy generation in the form of methane gas. 1.16 kWh energy is produced for every 1 kg of COD. Removal by anaerobic process. 3. Less biomass. Sludge generation. Anaerobic process produces only 20% of sludge that of aerobic process. CO plus H. O-soluble BOD. Aerobic process 0.5 kg 1 kg new biomass 0.5 kg ch. Gas. Biodegradable anaerobic process greater than 0.9 kg cod 1 kg new biomass less than 0.1 kg. Less nutrients. N and P. Requirement: lower biomass synthesis rate also implies less nutrients requirement. 20% of aerobic. 5. Application of higher organic loading rate. Organic loading rates of 5 to 10 times higher than that of aerobic processes are possible. 6. Space-saving application of higher loading rate requires smaller reactor volume, thereby saving the land requirement. 7. Ability to transform several hazardous solvents including chloroform, trichloroethylene and trichloroethane to an easily degradable form. Limitations of anaerobic processes. 1. Long startup time. Because of lower biomass synthesis rate, it requires longer startup time to attain a biomass concentration. 2. Long recovery time. If an anaerobic system subjected to disturbances either due to biomass washout, toxic substances or shock loading, it may take longer time for the system to return to normal operating condition. 3. Specific nutrients, trace metal requirements. Anaerobic microorganisms, especially methanogens, have specific nutrients, e.g. Fe, Ni, and company requirement for optimum growth. 4. More susceptible to changes in environmental conditions. Anaerobic microorganisms, especially methanogens, are prone to changes in conditions such as temperature, pH, etc. 5. Treatment of sulfate-rich wastewater. The presence of sulfate not only reduces the methane yield due to substrate competition but also inhibits the methanogens due to sulfide production. Effluent quality of treated wastewater. The minimum substrate concentration S from which microorganisms are able to generate energy for their growth and maintenance is much higher for anaerobic treatment system. Owing to this fact, anaerobic processes may not able to degrade the organic matter to the level meeting the discharge limits for ultimate disposal. Treatment of high protein and nitrogen containing wastewater. The anaerobic degradation of proteins produces amines which are no longer be degraded anaerobically. Similarly, nitrogen remains unchanged during anaerobic treatment. Recently, a process called ANAMMOX, anaerobic ammonium oxidation, has been developed to anaerobically oxidize NH to N in presence of nitrite, N plus 2H, ONH, plus NO. JE types of anaerobic reactors. TTTT low-rate anaerobic reactors. Anaerobic pond septic tank. Imhoff tank. Standard rate anaerobic digester. Slurry type bioreactor. Temperature, mixing, SRT or other environmental conditions are not regulated. Loading of 1 to 2 kg cod per cubic meter day. High-rate anaerobic reactors. Anaerobic contact process. Anaerobic filter. AF. Upflow anaerobic slugged blanket. UASB. Fluidized bed reactor. U hybrid reactor. UASB. AF anaerobic sequencing batch reactor. ASBR. Able to retain very high concentration of active biomass in the reactor. Thus extremely high SRT could be maintained irrespective of HRT. Load 5 to 20 kg cod per meter. D cod removal efficiency 80 to 90%. Upflow anaerobic sludge blanket. UASB. UASB was developed in 1970s by Leidinga in the Netherlands. UASB is essentially a suspended growth system in which proper hydraulic and organic loading rate is maintained in order to facilitate the dense biomass aggregation known as granulation. The size of granules is about 1 to 3 mm diameter. Since granules are bigger in size and heavier, they will settle down and retain within the reactor. The concentration of biomass in the reactor may become as high as 50 grams per liter. Thus, a very high SRT can be achieved even at very low HRT of 4 hours. NN. The granules consist of hydrolytic bacteria, acidogen, acetogens, and methanogens. Carbohydrate degrading granules show layered structure with a surface layer of hydrolytic, fermentative acidogens. A mid-layer comprising of syntrophic colonies and an interior with acetogenic methanogens. Upward flow anaerobic sludge blanket biogas T-Weir 3-phase settler separator baffles. Effluent gas bubble sludge granule sludge influent bed. FY anaerobic sludge granules physical, microbial, dense compact biofilms high settlability high mechanical strength balanced microbial community. Syntrophic partners closely associated high methanogenic activity. 0.5 to 2.0 g cod per gram VSS, d. Protection from toxic shock and the spaghetti theory of granulation proposed by Dr. W. Wiegand 1. Disperse methanogens. Filamentous methanosata ill. Floccule formation via entanglement ill. Pellet formation. Spaghetti balls. IV. Mature granules. With attachment of other anaerobic microorganisms onto the pellet. Anaerobic sludge granules, close up, YY. Anaerobic sludge granules. SEM. Acetate as substrate. Methanosata. UPA. Granular flocculant dispersed sucrose as substrate. Mixed culture. Effluent sludge bed influent effluent recycle expanded granular sludge bed and expanded granular sludge bed. EGSB. Reactor is a variant of the UASB concept. Cato et al. 1994. The distinguishing feature is that a faster rate of upward flow velocity is designed for the wastewater passing through the sludge bed. The increased flux permits partial expansion, fluidization, of the granular sludge bed, improving wastewater sludge contact as well as enhancing segregation of small inactive suspended particle from the sludge bed. The increased flow velocity is either accomplished by utilizing tall reactors or by incorporating an effluent recycle, an anaerobic contact process, ACP. Anaerobic contact process is essentially an anaerobic activated sludge process. It consists of a completely mixed reactor followed by a settling tank. The settled biomass is recycled back to the reactor. Hence ACP is able to maintain high concentration of biomass in the reablar bid thus SHI-QRCL. It respective of HRT. Degassier. A. 1 over US. CO. N fluent D if effluent CH. Egasiner completely mixed attached to sluddy ravshik may otherwise float to the surface. Recycled sludge waste sludge. Anaerobic filter copyright anaerobic filter. Young and McCarty in the late 1960s for treat dilute soluble organic wastes. The filter was filled with rocks similar to the trickling filter. Sent wastewater distributed across the bottom and the flow was in the upward direction through the bed of rocks * whole filter submerged completely. Anaerobic microorganisms accumulate within voids of media, rocks or other plastic media. Sent the media retain or hold the active biomass within the filter the non-attached biomass within the interstices forms a bigger flux of granular shape due to rising gas bubble, liquid. Non-attached biomass contributes significantly to waste treatment. Sent attached biomass not be a major portion of total biomass. * 64% attached and 36% non-attached. Upflow anaerobic filter heater biogas equals tilde. Effluent perforated equals I greater than Lao. Aluminum plate amping na port water bath. Tilde greater than peristaltic pump media. Plus C constant temperature sludge wastage feeding recirculation line tank at 4 degrees Celsius peristaltic pump. Originally, rocks were employed as packing medium in anaerobic filter. But due to very low void volume, 40 to 50%, serious clogging problem was witnessed. Now, many synthetic packing media made up of plastics, ceramic tiles of different configuration have been used in anaerobic filters. The void volume in these media ranges from 85 to 95%. Moreover, These media provide high specific surface area, typically 100 square meters per meter or above, which enhance biofilm growth. Since anaerobic filter is able to retain high biomass, long SRT could be maintained. Typically HRT varies from 0.5-4 days and the loading rates varies from 5 to 15 kilograms cod per meter *day. Biomass wastage is generally not needed and hydrodynamic conditions play important role in biomass retention within the void space. Multi-fed upflow anaerobic filter MUAF. Such feeding strategy has unique benefits. 1. Homogeneity in biomass distribution. 2. Maintenance of completely mixed regime, thus preventing short-circuiting and accumulation of VFA. Uniform substrate concentration within the reactor and prevent heavy biomass waste is fed through several points along the depth of filter. Effluent growth at bottom thus avoids clogging. 4. Effective utilization of whole filter bed SNS. UIOD 9. UTJOVEME. CAA. Market share granular sludge reactors at UASB at XBD hybrid OD Anaer filtho fluid. Bed B undefined EGSB plus UASB equals 72%. Options for post-treatment of anaerobic reactor effluents, beginning with a typical municipal raw wastewater. This level of treatment will generally result in an enhanced primary effluent quality. Intermediate between primary and secondary. Between 30 to 70 milligrams, I for BOD 5. Post-treatment should be designed to improve the effluent quality in the following parameters. Pathogen contamination, measured by the index of E. coli. Residual organic material, cod, BOD 5. Oxygen demand from the reduced forms of N and S. Residual suspended solids, TSS. Inorganic N and P. Nutrients. Basic types of post-treatment processes are pond systems, constructed wetlands, duckweed SA greater than mechanical aerated post-treatment. Indian scenario. The Government of India has made a major commitment to anaerobic treatment technology in its National River Basin Improvement Program. As of 1996, 13 new anaerobic treatment plants, with an aggregate treatment capacity of over 306 MLD, are under construction in India. The treatment plants described below have been in operation long enough to be able to evaluate their treatment effectiveness and their financial and economic costs and benefits. A 5 MLD plant in Kanpur, in the state of Uttar Pradesh, built in the late 1989. A 14 MLD plant in Mirzapur, Uttar Pradesh, based on the Kanpur pilot plant design, was commissioned in 1991. A 36 MLD plant in Kanpur reached full performance in 1994, treating a mixture of up to 75% municipal wastewater and 25% tannery effluent. The UASB process represents one important option for sewage purification in countries with warm climates, as it meets the above-mentioned basic necessities for a sustainable operation of wastewater treatment plants in developing countries like Cent low investment costs, Cent low maintenance demand, good performance, Cent low sludge production, Cent net energy production. References: Journal papers Makdar, Y. Sekaguchi, H. Samino, A. Ohashi, and H. Harada. 1997. Combination of a UASB reactor and a curtain-type DHS reactor as a cost-effective sewage treatment system for developing countries. Watt. Sci. Tech Volume 42 Nos 3-4 pp 83-88 IWA Publishing 2000. R. A. Barbosa and G. L. Santana Jr. 1989. Treatment of domestic sewage in an UASB reactor. Watt. Res. Volume 23. No. 12 pp 1483-1490, 1989. G. Lettinga, R. Roersma, and P. Grin. 1983. Anaerobic treatment of raw domestic sewage at ambient temperature using a granular bed UASB reactor. Biotechnology and Bioengineering. Volume 25, pp. 1701-1723, 1983. SMM Vieira and A.D. Garcia, Jr. 1992. Sewage treatment by UASB reactor, operation results and recommendation for design and utilization. Watt, Sci. Tech. Volume 25 No.7 pp.143-157, 1992. Sonia M. Vieira. 1988. Anaerobic treatment of domestic sewage in Brazil, research results and full scale experience, Anaerobic digestion, Volume 14 1988. Lalit K. Agarwal. Hideki Harda and Hiroyuki Okui. 1997. Treatment of dilute wastewater in a UASB reactor at a moderate temperature. Performance Aspects, Journal of Fermentation and Bioengineering, Volume 83, Number 2. 179-184.1997. Lalit K. Agarwal. Hideki Harda and Hiroyuki Okui. Cheng Seng. 1997. Treatment of wastewater in a UASB reactor at a moderate temperature. Microbiological Aspects, Journal of Fermentation and Bioengineering, Volume 83. No. 285-190.1997. Hideki Harda. Shigeki Uemura and Kiyoshi Momonoi. 1994. Interaction between sulfate-reducing bacteria and methane-producing bacteria in UASB reactors fed with low-strength wastes containing different levels of sulfate. Watt. Res. Volume 28 No.2 pp. 355-367, 1994. A. Schellinghout * and J. Calazos. 1992. Full scale application of the UASB technology for sewage treatment. Watt. Res. Volume 25 No. 7. pp. 159-166.1992. ARM van der Lasten G. Lettinga. 1992. Anaerobic treatment of domestic sewage under moderate climatic Dutch conditions using upflow reactor at increased superficial velocities. Watt. Sci. Tech. Volume 25 Number 7 pp. 167-178.1992. Lucas Segezo. Gritia Zeeman * Jules B. Van Leer. HVM Hamlillers and Gats Lettinga. 1998. A Review. The Anaerobic Treatment of Sewage in UASB and EGSB Reactors. Bioresource Technology 65. 1998. 175-190. Juan Carlos Parajo. Herminia Dominguez and José Manuel Dominguez. Biotechnological Products of Xylitol. Part 1. Interest of xylitol and Fundamentals of its Biosynthesis. Bioresource Technology 65. 1998. 191-201. H. Dragier. J. A. W. Moss. J. E. Shopman * and A. Kahn. 1992. Performance of the 5 MLD UASB reactor for sewage treatment at Kanpur, India. Watt. Sci. Tech. Volume 25 No.7 pp. 123-133, 1992. SMM Vieira, J. L. Carvalho. FPO Barajan. 1994. Application of the UASB technology for sewage treatment in small community at Sumer, São Paulo State. Watt. Sci. Volume .30, Number 12. pp. 203 to 210.1994. JHF Paraboom 1994. Size distribution model for methanogenic granules from full-scale USB and IC reactors. Watt Sci. Tech. Volume .30. No. 12 pp. 211 to 221. 1994. J. J. Bogti, A. M. Brewer. J. G. Van Andel and G. Lettinga. 1993. Anaerobic treatment of domestic wastewater in small-scale USB reactors. Watt. Sci. Volume 27 No. 9 pp. 75 to 82, 1993. Lalit K. Agarwal, Yasuhiro Ohashi, Etsuo Mochida, Hiroyuki Okui, Yasuko Ueki, Hideki Harda and Akiyoshi Ohashi. 1997. Treatment of raw sewage in a temperate climate using a VASB reactor and the hanging sponge cubes. Process. Watt. Sci. Tech. Volume .36 Number 6 to 7 pp. 433 to 440. 1997. SKI Sayed and MAA Fergala. 1995. 2. Stage UASB concept treatment of domestic sewage including sludge stabilization process. Watt. Sci. Tech. Volume 32. Number 11 pp. 55 to 63. 1995 Lucas Sagazzo. 2004. Anaerobic treatment of domestic wastewater in subtropical region. Thesis Wageningen University. The Netherlands with references with summaries in English, Dutch and Spanish. 2004 Cavalcanti. Paula Frassinetti Fitosa. 2003. Integrated application of the UASB reactor and ponds for domestic sewage treatment in tropical regions. Thesis Wageningen University. Wageningen, the Netherlands, with references. With summary in English, Dutch and Portuguese. Ziv plus 141p.